when we have this compound, basically we have the dihydropyridine, our work is almost done, DDQ to oxidize, and we get the target molecule. Okay? This is how we will do this exercise. Okay? Good. Normally, I recommend that at home do all the steps. I do it here very fast. First of all, because the whiteboard is not so big. That means it's difficult to do all the steps. But also because I guess that at this level, you have to know already how to do tautomerizations, imine formations, or any other small steps during the process. Okay? But at home, please do it step by step. If you have any doubt, if you have any question, please send to me. Okay, next reaction is we have this as a starting material, this ketoester, no, diketone, sorry, and we add this in HCl to generate this compound. Okay? How we can do it? Well, basically, if you take a look, this part of the final compound is basically this part, while this part here is basically this part. Okay, how we can do it basically is we take the diketone and we add this compound. In acid media, we protonate one of the ketones, which normally I will choose the one that has less steric hindrance, but it's the same, whatever we choose will work the same. Okay, and then the amine attacks here. We form the hemiaminal, and then elimination of the hemiaminal to form the imine. Okay? When we have this, basically, oops, sorry, here it's missing a methyl. Tautomerization imine enamine to generate this compound. Okay? And then what we can do is basically do a tautomerization here and convert this in this compound. Okay, it's a first tautomerization of imine enamine, and here we do a tautomerization similar to the tautomerization of imine enamine, but with this nitrogen to form this compound, this intermediate. When we have this, basically, the pair of electrons of the nitrogen attack the other carbonyl that previously we activate with acid, because we are in many acid, and we do exactly the same as before. Hemiaminal, elimination of water, and formation of the imine. That means that we generate this compound. Okay, if I am not wrong. Yes, I'm wrong. No, this is right, and this is right. Okay, we form the final compound. Okay, in the case that you choose the order, the only that you need to do is moving a little bit the electrons of the six-member ring. Remember that this is in equilibrium with this compound. The only that I did is moving the electrons. Like in the benzene ring, this is aromatic, that means that this is possible, that means, okay? Any of these two answers will be right. Okay? Good. Okay, then they say that we have this compound, this isoquinoline, and they say that we want to do this reaction. Okay, or we want to do this reaction. Basically, in both reactions, what we are doing is adding a bromine to an aromatic ring. This has to be done by an electrophilic aromatic substitution. Check the starting material. The starting material is a isoquinoline. Okay? If we check the isoquinoline, this ring is a pyridine, will be electron poor. This ring is a benzene, will be not electron rich, but at least more electron rich than not the pyridine. Okay, that means if we want to do an electrophilic aromatic substitution, what we will have is that the electrophilic aromatic substitution will happen always in this ring, in the benzene ring, in the electron rich ring, the more electron rich ring, while will never happen in the isoquinoline. Okay? Then what we can do for the first, this is easy. What we add is we can add bromine, iron tribromide, and probably we will get a mixture of these two compounds. Remember that the active positions in the case of isoquinoline for the electrophilic aromatic substitution are these two positions of the fused aromatic ring, the fused benzene ring, and we will get a mixture of both. We cannot select one of the two positions. But okay, it's what we want, that means this is very easy. Now, how we can do electrophilic aromatic substitution in the electron poor ring? And now what you have to remember is how we make pyridines appealing for the electrophilic aromatic substitution. Remember, if we have a pyridine, how we activate a pyridine? How we activate a pyridine for the electrophilic aromatic substitution? Basically, what we do is do the pyridine N oxide, isn't it? Here we will do exactly the same. We take this compound, we add MCPBA, and what we generate is the N oxide, and then this compound now is very active against the electrophilic aromatic substitution, and remember, the orientation is always para. That is what we want. We add the same bromine plus iron tribromide, and we get this compound and then simply PCl3, and we remove the N oxide to form the final isoquinoline, the final quinoline. Okay? What we learned in this last exercise is when we have fused rings, pyridine plus benzene, also this is working with indoles. If we want to do electrophilic aromatic substitution, this is always will happen in the electron rich ring. Remember indoles. Okay, in the case of indoles, which is the electron-rich ring, the p-role. That means the electrophilic aromatic substitution will take place in this or this position. Here is just the same. We have a pyridine and we have a benzene ring. Where will take place the electrophilic aromatic substitution? In the electron-rich ring, that in this case will be the benzene. Okay, and then remember that if we want to activate a pyridine for electrophilic aromatic substitution, what we need to do is to form the N-oxide. Okay? Thank you very much for your attention. Okay, and now what we will do is the exercise 1. That is, draw the products of the following reactions justifying your answer. Okay? We have this compound. And we add sodium methoxide. 1 equivalent. What will happen? Basically, we have a pyridine that is a compound that is highly activated for the nucleophilic aromatic substitution, and we have a very good nucleophile, a methoxide. What we will do is basically a nucleophilic aromatic substitution, and we can choose ortho position, meta position, or para position. Which one we will need to use to do the attack? Okay, it's a pyridine, that means that are activated the ortho and para positions. And normally the ortho position is slightly more active, is more active than not the para position. But what's happening? Which is the better group to do aromatic, nucleophilic aromatic substitution? The better group is the fluorine. Why? Because fluorine is very small, allow the approach of the nucleophile very easily, and also it's very electronegative. That means it's favoring the attack of the nucleophile at this position. That means if we want to do a reaction, this is rejected because it's a meta of the pyridine. This is rejected because even if it's in the most active positions, it's a bromide, will not be so active as a fluoride. That means that substitution will take place in the para position. The final product will be okay? If you're asking me why will have this and this will not evolve to have more substitutions, basically this is a more electron-rich ring than not this because we have the methoxide. Okay? Here is the same. Okay, here we have two possibilities, chloride and this chloride, to do a nucleophilic aromatic substitution. Which ring is more electron poor is what we have to answer in order to do this reaction. Well, here we have a benzene with a ketone, here we have a pyridine with a ketone. Obviously, the most electron poor ring will be this. That means that the attack will take place in the pyridine ring. Final product will be okay, the substitution in the electron poor ring. Next, we have this compound. And again, what we are doing is nucleophilic aromatic substitution. Okay? That means the only two possibilities is where are the two halogens, here or here. Where will take place? Again, we will need to choose the ring that is more electron poor. Here is a pyridine ring, here is a phenyl ring. That means that the reaction will take place in the pyridine ring, that is the electron poor ring, and what we will have will be okay. Good. Next, we have this ring. And we add bromine, iron tribromide. What will happen? Well, what we have now is a electrophilic aromatic substitution. That means the first thing that we need to determine is which is the electron-rich ring. We have here a pyridine, here a benzene ring. That means that the benzene is more electron-rich than the pyridine. The reaction will take place in this fused ring, in the benzene fused ring. And if we remember, which are the active positions of the quinolines in the electrophilic aromatic substitution, we will have these compounds. Okay. The active positions are these two. Okay? Next one, what we have. We have this compound, okay, and we do exactly the same reaction. A bromination, electrophilic aromatic bromination, and again we have to decide which is the electron-rich ring. In this case we have a pyridine with a ketone, and here we have a benzene ring with a ketone. Obviously the electron-rich ring will be this, and because this is an electrophilic aromatic substitution, what we need to do is to know in which position we'll attack. This is a electron withdrawing group, that means that we'll orientate meta. The final compound will be the addition in the meta position of the benzene ring. Okay, next one, we are doing the same, but this time we have this compound and we do the same reaction. Again, we have to choose the electron-rich ring as in the example before, and for exactly the same reasons. This is the electron-rich ring, okay? It's the benzene ring that is more electron-rich than not pyridine. And then we have to decide in which position will take place the substitution. And obviously this is an electron donating group. Don't be mistaken because it's an oxygen. The pair of electrons can delocalize inside the ring. That means that will be ortho-para. Normally, for aesthetics reason, para is more favorable. That means that the final product in this case will be okay. Check the difference here because we have a ketone is meta. Here because we have an ether is para. Finally, we have this compound and we add butyllithium and then benzaldehyde. What is happening? First step, we add butyllithium. It's a very strong base. We have to decide which is the most acidic proton here. The most acidic proton is the proton in the metal position, okay? And what we do is to generate an anion here that will attack the aldehyde to form after hydrolysis. This alcohol compound. Okay? That's all for the problem class. Please, if you have any question, any doubt, send me an email. We can organize a meeting. If I cannot ask directly from email, we can organize a meeting by Teams, by Blackboard Collaborate, whatever you prefer. Okay? Here in this last exercise, the most important that we learn is how to differentiate the rings when we are doing electrophilic aromatic substitution or we are doing a nucleophilic aromatic substitution. Yes? In electrophilic aromatic substitution, the reaction will take place in the most electron-rich ring. In the nucleophilic aromatic substitution will take place in the more electron-poor ring that has the leaving group, the halogen, in his ring. Okay? Thank you very much and see you soon.